You might have stumbled upon previous entries from half a year ago, or maybe this is just a random video you found accidentally while searching for a new wallpaper in your living room. In any case, you're probably wondering, what the hell is this? The last video that I posted on Neuro-Evolution and neural networks weren't very expressive. That is because they were for documentation purposes, documenting failure for the most part. Regardless, the project is back, as am I, with fresh ideas and a few words to spare for the occasional passerby. To many, the whole field of artificial intelligence is little more than an academic exercise, but sooner or later, machine learning will become something we will all have to deal with. In fact, it's happening already. I find the topic intriguing, so I research, I experiment. It's a wonderful way to kill the time. Most likely, the foundation of some advanced AI will be a software or hardware-based neural network. The concept of neural networks isn't new. They've been used for decades to solve optimization problems, and they work, but they're limited. Mostly limited by static topology. Improving the performance beyond tweaking connections and weights, for example by incorporating it into an evolutionary algorithm, has great potential, but proves difficult. Just like a brain, a neural network is a delicate apparatus. It cannot be cut in half and glued back together. They call this the problem of competing conventions. Two brains, which do the same thing, may exhibit a very different structure. Recombination at the wrong spot will usually result in severe brain damage. Whatever fitness there was is ruined, and the crossover becomes no more than a destructive mutation. So how do we solve this then? First off, a neural network can be interpreted as a directed graph. Given two related graphs with arbitrary topology, there is no way to tell which parts belong together. So to circumvent that problem, I forced the graph into a different structure, the genotype, in particular a binary search tree. That's what you're looking at. So one half of the network branches off to the left, the other half branches off to the right. The tree node becomes a hub that manages the connections between the two halves. Based on the assumption that the networks are related, I can conclude that both left sides and both right sides should do the same thing, in theory. This makes recombination easier because now I only have to deal with half of the network and I can apply the algorithm recursively. A while ago, I patched together a quick prototype to see if and how performance could be preserved throughout generations by baking the output into an image. And even though the experiment wasn't a total disappointment, I wasn't quite satisfied. Too often, the recombination would result in degenerated offspring. This was partly due to a badly tuned activation function, but also because the crossover operation misbehaved exactly as described. This demonstration follows the same idea, but uses an improved interpolation algorithm. The two genotypes, left and right, are mutated randomly and are not related. The genotype in the middle is generated by smoothly interpolating between the other two, back and forth. Keep in mind, this is a pretty brutal test because under normal circumstances, the two parents would share some genetic ancestry. That's why the interpolated genotype often looks somewhat pale. In the next step, I'll use the genotypes to generate the phenotype, which will represent the actual neural network. You can see what those look like in the previous videos. As usual, I'm going to let this run for a while to collect some data. See you soon.